So let's get started, everyone. So welcome back. So today we're talking about confidence intervals. Hold on. So great. So today we're talking about confidence intervals. So this is going to be kind of an extension of the statistics part that we started. So last week, I'm going to start by reviewing a little bit about estimation. Confidence intervals gives us more information in addition just to the the estimate, just the parameter estimation that we talked about on Thursday. If you see the schedule, I've got 3 lectures devoted to this. It's probably kind of in terms of if you look at the notes, how much we covered, maybe 2 lectures worth of notes, but I'm going to try and go kind of a little bit more gradually through this concept. I guess it can be a bit slightly harder to wrap your head around, I guess, than some of the other things. So we'll maybe go through this a bit more gradual. If we do happen to get through it really quick and everyone seems to be understanding it, maybe we'll finish in 2 lectures. But so the plan is 3. Okay. A couple of announcements. Let's see. So homework 4 is almost graded. Usually this is the day by which we get the previous homework graded. There have been a few delays for various reasons. So homework 4, I think it'll be done graded tomorrow, it seems. Homework 5 is listed as being due today on the webpage. We have moved this back by 1 day. There are a couple of things that happened. There were a bunch of some office hours that started late. A couple were canceled or moved. And we didn't have Gradescope open. And I was somehow missed a lot of discussion on Canvas. So we've moved the due date back for homework 5 1 day. If for some reason, if people make a really good case that it needs more than 1 day, maybe I'm willing to listen, but I think 1 day should be okay. Just announced on Canvas, we're going to have an extra office hours tomorrow. Usually Austin has his office hours Wednesday from 3:30 to 4:30. He's going to extend those from, let me write this. Here's so you can see it. So on Wednesday, March 29th. TA Austin is going to have help hours from 3:15 to 4:30. These will be in the normal room that he has them in, 3115, and then he's going to keep going from 4:30 until 6. And for scheduling reasons, he's going to need to move to 3105. This was just posted on Canvas. So now the homework was a homework 5. It's not going to be due until the end of the day on Wednesday. I'll also be available today after class to answer questions. I think Ananya's office hours have been moved to today. I think there's also Tuesday, March 28th. So that's today. TA Ananya is going to be from 7 to 9 p.m. I think this was on Zoom, right? Did she post that was on Zoom? Yeah, so hers are going to be on Zoom. There are a few things that happened. We had to move some stuff around. So I apologize for that. but hopefully there's still enough places to get help hours if you have questions, and I'll I'll be a bit more responsive on the discussion boards than I have been. So hopefully we'll get back to the regular schedule for the assignments for the rest of the semester, but we'll yes. Okay, so questions or concerns about that? Yeah, so okay, great. Oh, this mic is on. I think I speak loud enough without the mic, right? Yes. Okay. Great. So we're gonna. Is there anything else on the schedule? Yeah, I think that's all I have to discuss now. So what we're gonna talk about. So confidence intervals. Let me review estimation first. Review estimation. Okay, and that's where you assume that there's some distribution f of theta, right? So this is the PDF of some unknown probability distribution, and this is the parameter. Okay, we'll assume there's just one parameter. We'll just there could be multiple parameters. We'll assume there's just one parameter at a time that we're going to be concerned about. And so we're assuming we have this distribution, and then we also assume that we're going to have these observations x2, x1, x2 up to xn, which are IID from from this distribution. Now, these are not realizations. These are not actual data we're thinking about here yet. We're thinking about these as random variables, right? So these are random variables, okay? And then we're going to create. So then we're going to create a statistic, okay, which we're going to call theta hat, which is some function of these random variables. Okay, so again, theta hat is another random variable. That means it has a distribution. And so what the estimation is going to be looking at is how close does the random variable theta hat approach the true parameter, so theta, right? Because once we've assumed a shape of a distribution, whether it's a normal distribution or something else, all we need to describe it is just the parameter. We get the full continuous modeling of the distribution once we know the parameter. And so we're trying to estimate this parameter, and we estimate. So we often estimate. So we'll kind of estimate. So often. So we'll call. Let's see. So I get the notation right. We'll call theta hat the estimator, and we'll say that this is an unbiased estimator if the expected value of theta hat, remember it's a distribution, is equal to theta. Theta is is like a constant value, right? So theta is an actual scalar value. Could be vector value in some case. For here, it's the scalar value, just one kind of actual constant. And where theta hat is a distribution, so we say, well, if the expectation of it is exactly theta, then this is good. This is an unbiased estimate. We talked about, then you could think about like the variance of this estimator. If the variance is small, this is good, right? If it's unbiased, if this bias, the difference between these two values is zero. All right, so how would we actually use this? We would use it if we have these random variables, right? We have the random variables. This is kind of a modeling of the problem. We haven't done anything with actual data yet. So we might want to, when we actually get data, we're going to get like these realizations, okay? So these x1, x2 up to xn, and these are lowercase. So that means that when I use lowercase variables, that means those are realizations. That would be the actual data that we played with in R, and we plotted the actual data, and we can compute that estimator. We can put those actual data points through the function. It could be just taking an average of those, those values, and we could say, well, that's just going to give us a single value that is we're trying to use to estimate the true value of the parameters, but we can't say anything about that value. That value is what it is. I calculate it's like 17.3 or something. Is that a good value or not? Well, I say, I know if I modeled it from this process, then I would say, well, if this was a random process, then the expectation of that random process matches what I actually want the value to be. Okay, so once we get the actual data, we can't talk about the probability anymore. We can talk about the probability of a process. And so when we run that process, we know probabilistically how good that process is, right? So in like some sense, and here we want it to be unbiased. Basically what we talked about. All right, so we kind of said if it's unbiased, that's good. If the variance is small, that's good, but we kind of aren't saying how close is the estimate on actual data to the right parameter value. We haven't really quantified that in a real sense. Remember, the variance is also kind of an expectation. It's the expected squared deviation, right? But it's not actually telling us how close is it to the right answer. Yeah, and back. Well, yeah, so we can say an estimator is good with respect to, it's good with respect to an assumption on the distribution. Okay, so if we assume the data came from this distribution and we wanted to then model that distribution via its parameters, then this way of combining those random samples from that distribution together would give us a good estimator in the sense it's going to be unbiased. Its expected value is the true value, assuming the data came from that distribution. Okay, yeah. Yeah, so we do have, so you said we don't have a good way of knowing what the distribution should be. I would say we have a pretty good way of making a hypothesis or a guess of what the distribution should be. We'll go through some examples, I guess, in this lecture and in the next lecture. But if the events that you're modeling are like binary, it's either something happens or it does not happen, we can use like a Bernoulli distribution, right? We assume that there's a fixed probability that something happened. I flipped a coin, it landed on heads or so it didn't land on heads, right? Okay, there's some crazy situations. It could land on the edge, or a big gust of wind comes and it blows the coin away. I mean, but basically it happens or it doesn't happen. And if you assume that's the same every time, that's a Bernoulli distribution. Okay. If you assume it's some continuous value that you could measure that's bounded away from zero, probably, right? Like the amount of snow that falls in the winter, right? This is probably going to be a good model as a normal distribution, right? So like we kind of can do a pretty good job of modeling these things, and it's not exactly perfect, but these things are, they're going to be fairly good, right? They're pretty good. They're not perfect, and it's not something where you can, you're given like an API, you need to write code that matches exactly that API. You need to use some common sense knowledge and some modeling. But we can do a pretty good job about that in a lot of cases. Okay, but it takes some you have to think about it a little bit, right? So we'll see some examples throughout the rest of the semester that will help make this clear with the distributions we've seen. Sometimes you'll say, well, the data doesn't really look like that distribution. It looks like something slightly different. And there's probably someone came up with a distribution that fits what you're interested in, and you could look it up on Wikipedia. This class is not going to go through the litany of all possible distributions I can think about. We'll give you kind of ones that will handle stuff like 90% of the time, and the last 10% has a long tail that is in like Wikipedia and stuff that you can try and discover over time as you need them. Yeah, great. But that's it's a good question point to think about. Yeah. So okay, I guess one example that I just kind of wanted to go through just a bit that we didn't go through at the end of last lecture is, so let's say we have some, so I'm going to flip a coin. So it's got, so two sides, and I'm going to flip this n times. All right, and I'm going to say the sides are a 1 or a 0. Okay, so just label the sides 1 or 0, and so these flips are going to be F1, F2, so like up to Fn, right? So these are the flips I'm going to do. I haven't done these flips yet, so I'm thinking about this process. Okay, and it's going to give me either a 0 or a 1, and say those are the only possible outcomes. I assume these are IID flips, right? So they're IID, okay? That means that they're independent. What the second flip has no influence on what the fifth flip was, okay? They're going to be so correlated with each other, right? Well, they're going to be, they're not correlated. They're independent of each other, but they're from the same distribution. They're all giving me information on some sort of distribution. I shouldn't use, well, let's use uppercase F. It should be okay. And so this is from some distribution. What distribution do you think this would be from? Like, what's a modeling of this distribution? Bernoulli. Yeah. Okay, great. So this is, I would say, from a Bernoulli distribution, right? This is exactly Bernoulli as I described it. It's going to have one parameter P, right? That's the probability of getting a 1, right? This parameter maps to the probability of a 1 under this distribution. Yeah. Yeah, so the Bernoulli distribution is a discrete distribution, right? That the outcome of it is either 0 or 1. Okay, and it's parameterized by P. P is the probability of getting 1s. 1 minus P is the probability of getting a 0. Okay, right. So we just have this P. Okay, and now I would like to create an estimator of P from the random variables. Right? Well, what would be a good estimator of P from these random variables?
Yeah.
Okay, so you want to plot the plot the CDF, and then do. Oh, so look at the largest and smallest values, right? So think of an estimator as like, I'm going to collect data. I'm going to write a function. I'm going to write some code that's going to take in that data and output a single value, right? And so you're suggesting, and so this is fine, that I want to write a function. So I want to calculate the min of F1 up to Fn, and I want to calculate the max of F1 up to Fn, and I want to then return max minus min divided by 2, right? I mean, this is a reasonable thing to do, right? If this was from if I thought this was from a uniform distribution, right, this would actually be the right thing to do. Yeah. Yeah. The problem is it's almost always going to give almost always 0, almost always 1, right? So I'm probably going to get 0 or 1, and then the max plus the min, yeah, max plus min divided by 2. That max plus min divided by 2 will almost always be 1/2, right? So this probably is not going to be a great estimator unless P happens to be 1/2, right? If I have a small number of flips, this might actually, if I have one flip, or if I have 2 flips, this might actually be interesting, right? If I have 2 flips, it might actually give me something that's not always 1/2, because you might get 2 1s or 2 0s, and those probability differ, right? But this is not the thing I was looking for, but this is a valid statistic. This is a valid estimator. It's not going to be unbiased in general. Okay, great. But that was a good example to walk through. Yeah. Yeah, so every random variable is a draw from the Bernoulli distribution. It's one flip. If I took the binomial distribution, I would have one random variable would involve taking n flips and adding up their values. Okay, but so if I flipped, let's say I had like 10 copies of a coin, or like let's say I had 8 copies of a coin. I said all the copies I think are the same. They all came off the same machine. Each coin I'm going to flip 10 times and record the number of heads. Okay, that'll give me a value for each coin, and then I have 8 random variables. Each random variable is the outcome of the 10 flips of one coin. All right, so I could, that would be a bunch, that would be n draws, 8 draws from a binomial distribution, but each, now I'm just doing one flip. So each random variable is just one flip. That's Bernoulli. Yeah. Okay, yep. Yeah, great. Good. So let's get another function here, right? And these are functions of F1 up to Fn. And here we're going to do a different function here, F1 up to Fn. And I'm just going to return 1 over n, I equals 1 to n, the sum of f of I, right? So this is the average of all of the values, either 0 or 1. Okay, good. So this is the estimator I was thinking about. Okay, so the output of this function, let's call this the average, so function, f1 up to fn, so just to distinguish it from the red one. And so we'll get the outcome will be p hat, which will be the average function of f1 up to fn. Okay, so this is going to be an estimator. I could have gotten an estimator the same way from the red function. That would have been an estimator. Okay, but I like this one better. I like this function slightly better. Why would I like this function better? What do we know about it? And back? Variance is lower. I'm not sure that's true. I mean, if n is large, probably the red function has a lower variance. It's almost always going to be 1/2, right? So that's expected squared deviation from the expected outcome of the function. If it's always 1/2, the expected deviation is probably close to 0. So the red function probably has a lower variance. So that's not the thing I like about the purple function. What do I like about it? Okay, the red one's kind of doing that too, right? It's looking at all of them and deciding which one's the min, which one's the max. If I was drawing from a uniform distribution instead, the red function is actually a good thing to do because it looks at all of them in this way. You could use, actually the purple function would work well for looking at the mean of a uniform distribution. I don't know which one is better actually, offhand. Which one is a better estimator of the uniform distribution? Probably the purple one, but we'd have to do some calculations. Yeah. You can use the purple one. Sure. Okay. But I know it's a coin, and I want a Bernoulli distribution. I want to know p. I'd like to estimate what's the probability I get heads. It might not be a fair coin. So why do I like the p hat from the purple distribution, the average distribution? Yeah. Yeah, the expected value, p hat, is a random variable because it's a function of random variables, and the expected value is exactly p. P is the probability I get. So one, I can actually write up, I know the expected value of each fi is equal to p, okay? And by the central limit theorem, I know that x bar n, which is equal to p hat, has expected value of x bar n, which is the average of a bunch of IID, so random variables, has the same expected value of one of those. Yeah, should call this fn bar here. Let's say fn bar is the same expectation of any one of those random variables, which is exactly equal to p. Okay, so I know from this that the expectation of p hat is exactly equal to p. So that means it's, what kind of estimator is it? It's an unbiased estimator. Okay, so this is an unbiased estimator. It gets the right expected value. Okay, if I had a 75% chance of getting a heads, right, then p would be 0.075. Whereas if I use the red estimator, the red estimator function, I'm probably going to get an expected value of not quite 1/2, but probably, if n is large enough, it's probably going to be pretty close to 1/2, right? So that's not going to have the right expected value of that distribution. So this one is favorable in that it's unbiased. All right. Okay. So most of what we want in an estimator is going to be an unbiased estimate. For most of what you do, that's going to be the case. So occasionally, you'll eventually look at trading off some, adding a little bit of bias to reduce the variance, but not necessarily as much bias as you might be adding in the red estimate, because the variance could be much smaller there. So, okay, but that'll be outside of this class. So, okay, great. So this is estimation. This makes sense. You're going to, yeah, on the next homework, you're going to have to do some estimation. I think there's going to be one easy problem and one kind of a little bit, the one tricky problem will be having to do with some estimation. So questions about this is a good time to kind of ask, or maybe once you see the homework out Thursday. Yeah. Yeah. Okay. So the purple function does not returns a random variable. The random variable has a distribution. That random variable is an estimator of the parameter p. The parameter p happens to represent the probability of 1. Okay, so there's a lot of the fact that it's p makes this kind of confusing, but it's actually a random variable, and there's a PDF of p hat that you could try and calculate. By the central limit theorem, you kind of know as n gets big, it approaches a normal distribution, right? But the important thing is the mean here. Okay. The outcome of the red distribution is also an estimator. It's also a random variable. Okay, so it just does not have the unbiased property. So that's why we're not going to like it as an estimator. We like unbiased estimators in this class. All right. Okay, we want an estimator, which is a random variable, and we want to look at its expected value. If it matches what we're trying to estimate, then it's unbiased. Okay, good. All right, let's go on to confidence intervals. Okay, these are going to kind of be working with kind of thinking of taking a random sample, which we're going to represent as random variables, and instead of just looking at the expected value, we're going to we're going to ask probability questions about the random variable, about those estimates. Okay, so this is going to assign probabilistic. So guarantees about estimators. Or so usually we'll actually say this about well, instead of estimators, you can kind of think of a dual about this with estimators. I want to say about parameters. Okay, so yeah, I want to say parameters. This you can kind of do some like algebra and say it about the estimators as well, but we're going to say something about the parameters. We want to say we have an estimator and its expected value matches that of the parameter, but instead we want to say, well, the parameters are with some probability going to be in this range. We're going to say some statements. So we're going to have x1, x2, xn, which are these IID samples from some sort of distribution. and we're going to create, create two, so statistics, okay, LN and RN. Okay, these, again, a statistic is going to be a random variable. So LN is going to be there's some function we're going to call of x1 up to xn. Okay, and so this is going to be it's going to be it's going to be a random variable. Also, Rn is also going to be a random variable, and we're going to have the property. We're going to say something like the probability that the true parameter is going to fall in between these two. So these two statistics. Okay, we're going to say the probability is equal to 1 minus alpha. Okay, so a confidence interval, the confidence interval, this is called the 100, 1 minus alpha, so percent, so confidence, so interval. Okay, that range between ln and rn. Okay, so we want to create these statistics, ln and rn, so that the probability that the real parameter falls in this range is equal to 1 minus alpha. Alpha would typically be, so we'll think of alpha is equal to like 0.05, some small value. So a common example is a 5% or a 95% confidence interval. Okay, if we set alpha equals 95, that gives us a 95% of the confidence interval. All right. Yeah, it's a question. Yep, sure. Yep, that's the usual thing, right? ln's on the left, rn's on the right if you're facing the screen. So, yep. Yep. So theta. This is the parameter that controls the distribution that we're kind of trying to estimate. Okay? Okay, so I've drawn a probability here. Oh. I've written down this probability. Okay? And I want to calculate this. I say it's equal to, say, 0.95. So I want this to be a large probability. Probability indicates something random. What's the random part here? What's the random part of this probabilistic statement? No. Okay, good. This is a good point, but this is a common kind of confusion about this. Theta is a constant. It's a parameter. Okay? This is a constant, so parameter. Okay, so that there's nothing random about theta. We assume there's a ground truth theta. This is kind of like the ground truth. Okay, we don't know what it is, but we assume the data's come from some distribution, like the Bernoulli distribution. If it's a coin flip, it has to be like the Bernoulli distribution if the coin is the same every time you flip it, right? But we don't know what the parameter, what the probability it is heads. That is a truth of nature. okay? And we want to know something probabilistic about that. So that is not random. That value is fixed. It's just not known to us. Okay, so this is good. This is exactly the confusion I wanted to see, and then tell you that it was not the right way to interpret it, because it's the most common. The first thing you interpret, you look at this, you think, oh, the theta is random, right? And I need to get some values. Okay, so the theta is not random. So what is the random part here? Well, how do I define the probability over? What's left? Yeah, so the L sub n and the R sub n, those are random variables, right? R sub n is a random variable. L sub n is a random variable. These are random variables. They're a function of the random variables x1 through xn. These are the observations I'm going to make that I haven't made yet, and they're going to pass through some random process, which is f of theta. And they're going to come out. That's going to be where the randomness comes from. I have some function I do to calculate L of n and R of n from those random variables I haven't seen yet. And so that's why those are the random part that the probability is over. Okay. Okay, so we're in this class, at least for now, there are two random variables, which means I need some sort of joint probability distribution, and this starts to seem complicated. We're going to think about distributions which are going to be, we're only going to need to calculate that. For instance, they'll have like, we'll do something, so we just have to calculate one, and the other one is going to be symmetric. Okay, so we only really need to worry about one of the random variables, and that'll account for alpha over 2 probability of it being too far, and the other alpha over 2 will occur on the other side. Okay. Yeah, so the L and the N are the random variables here. That's the randomness, and that's what the kind of the probability is over. So okay, so let's start. We're gonna, I guess today we're gonna look at when the distribution, we're going to assume, we're gonna look at, so confidence, so intervals for normal, so random variables, with a known, so variance. Okay, so we're going to assume we know the variance, but we have, so we have normal, so random variables. Okay, so we're going to say that x1 up to xn are these IID draws from a normal distribution with parameters mu and sigma squared, but we're going to assume that this guy is so known. We know, we're going to assume we know the variance. Okay, a little bit later on, we'll see what happens if we don't know what the variance is. We'll have to do something slightly different. So okay, so we're going to assume that we know the variance, and so we want to kind of get some estimation or some confidence interval in this case on mu, right? So this guy is going to be so unknown. Okay, so mu is going to be the unknown. That's the theta that we're trying to estimate. All right, so think of this as the theta value. Okay, so we're going to draw data from this random variable, from this distribution. We're going to assume it's a normal distribution. It's something like if I was planning for this lecture and I was going to go through an example, I'd say, I think the amount of time it's going to take me to walk through this example is going to follow a normal distribution. And if I gave the same lecture 10 times, you would get 10 kind of independent estimates of how long it takes me to go through an exam. Okay, and so that might be a normal distribution. Yeah. Well, yeah. Well, so I might not do them this. If I teach a class for for 10 semesters, right? That it's kind of. I mean, there's some classes I've taught like 8 times, right? And you switch it up a little bit, but some lectures, some examples you do like 8 times, 8 or 10 times. It's okay. You got to do something to keep it fresh. But I haven't taught this class this is only the second time I've taught this class. So I've done probably these examples before, but it was like 7 years ago. So probably fairly independent. Okay. So you might get 2 random variables. That's n is 2. Okay, that's enough to work with. Okay. But think about the next 8 times I teach this class. So okay. Yeah. As a teacher, you tend to teach the same stuff multiple times, and it's not as bad as it sounds. So yeah, well, the students are different. All right, so it makes it, that's where a lot of the randomness comes in, right? You ask a lot of questions. It's okay. Don't mean to accuse you of anything, but it's good to ask questions. Sometimes there's not someone who's asking all these questions that, Okay. Okay, what do we know from the central limit theorem? Okay, we know that we can compute this, we can transform this into this Zn value. So this is Xn bar, right? The average of these minus mu sigma over square root of n. Okay, and that these Zn's follow a normal distribution. Okay, so I can take the Xn bar, I can subtract mu, divide by standard deviation over square root of n. This now comes from a standard normal distribution, right? Okay. So so I want to convert it into this because then I kind of know what the values are for a standard normal distribution. So I want to think about converting my random variables in this way, and I can study this distribution, and I can kind of know some actual constants ahead of time, which will be so useful for common choices of, so alpha I'll use for these confidence intervals. So in particular, if I have a standard normal distribution, I can say I want some probability that Z alpha over 2, negative of Z alpha over 2 is less than Zn is less than, this is lowercase z alpha over 2, right? This is equal to exactly, so 1 minus alpha. Okay, so the reason I converted this into the standard normal is that what's the property I have of this standard normal is that if I plot this and I have this is the PDF of Zn. Okay. What do I know about the mean? Yeah. Yeah, the mean is exactly 0 here, right? It's exactly 0. And then I want to draw a confidence interval around here, right? What does the confidence interval look like here? Yep. I don't know the exact value, just kind of a general shape. Yeah. Yeah, this confidence interval, okay, so I kind of want to put some stuff out where it's thin, and that's where the low probability is, right? these values, Z alpha over 2, I kind of want to choose them, Z of alpha over 2, right? I can choose them so that these are so symmetric. I can go out in either direction, and then what I want is at these tails, this area under the curve out here. What is this area? What's area under a PDF represent? Just in general, and part of an area under a CDF represents is it a random variable? Is it a constant? Is it, what if I integrate part of a PDF? It's the probability, right? So an area under a curve, this is so probability. This area is equal to some, so probability, okay? And so I want to choose those green values, Z alpha over 2, so that green part under the purple curve, under the PDF, has a particular probability. What probability should I choose? Well, in terms of alpha, its parameter is by alpha. Yeah, so 0.05. I want both of the areas together to be 0.05. So this one should be equal to alpha divided by 2. I want the probability under that one tail on that one side is equal to alpha over 2. And this one, the area, is also equal to alpha over 2 on this side also. Right, so if I add them up, that's alpha probability of being far away from, I mean, that's the total probability outside of this interval is going to be kind of total of 0.05. Yeah, so maybe I misspoke and said so CDF, but an area is the area under a PDF. So if I integrate a PDF, when you integrate kind of a curve, you're measuring the area away from the 0 line, right? All of our PDFs have values greater or equal than 0. And if I integrate over all of the values, it's 1. Right? And if I integrate over part of the values over an interval of values, that gives me a probability that the random variable, Zn, falls in that interval. Okay, so if I look at this interval this is the interval now from, this is from negative Z alpha over 2 up to Z alpha over 2, right? That orangish color, that's my fourth color I can highlight with. The orangish color, that interval, what's the probability that the Zn random variable falls in this interval? Yeah, great. The area under the curve for that orange interval is 0.95, right? So 95% of the time, a standard normal random variable with mean 0, variance 1 falls in this interval 95% of the time. Okay, so I would like, so if I know that my random variable is a standard normal, then I can pick these Z alpha over 2 values, which I can pre-calculate, and that gives me a confidence interval. Okay? Yeah. Well, I'm telling you, that's how I define Z alpha n. Okay, yeah. So I'm telling you, if the area under the green part of the curve on one side is alpha over 2, then that defines Z alpha over 2. Yeah. So those are the ones. I guess this is not exactly confidence interval. These are flipped. The Z alpha over 2s are constants, and the random variable is the n here, right? For confidence intervals, I have this the other way around. But if I have this random variable, I can in fact calculate these z alpha over 2s. Z alpha over 2 is exactly is equal to the 1 minus alpha over 2. So the quantile of the the normal distribution, the standard normal distribution. And it turns out that z of 0.025, that's if alpha is 5%, right? Then this is approximately 1.96. And if for z equals 0.005, so that's if alpha equals 1%, that's another common value, right? Then this is going to be approximately 2.58. Okay, so these are kind of just values to know, right? If I have alpha equals 5%, then the z alpha over 2 is about 1.96, right? If I have alpha is 1%, then the z alpha over 2 is 2.58. These are things I don't expect you to totally memorize these things, but if you were to calculate them, you're basically looking them up in a table. And since these are really common choices of alpha, someone might actually hard code them into some sort of stuff they're doing. If you actually wanted to calculate this in R, right, you're going to be, just here, right? You can, again, you can draw the, this is the standard normal distribution. And you have this function, this quantile function. If I do Q norm of 1 minus 0.05 times 0.5, right? Because I divided it in half. That's 1.195996, about 1.96. Okay, so this is the z alpha over 2. Alpha was 0.05, and I divided it by 2. I multiplied by 0.5. Right? If I wanted the 1% kind of associated value, I get about 2.5. So 7. So 0.58 about. Right? So somewhere in there. These are just values I would do. I can plot here. Here's a plot of this. So like CDF, right? I want to pick out a value that has, there's only kind of, so I'm saying, yeah, so I'm picking out a value where 97.5% of the mass is less than it. So I pick 0.975. And up here, and I get a value, this is about 1.96, right? So that's this value here. So you can plot this. This is something that's pre-built into R, okay? So, okay, so just to show you where I got these values, okay. Okay, so I'm gonna use these values now to calculate the confidence interval for when I draw stuff from the normal distribution with the unknown mu. Okay, so I'm going to need to use these now. Okay, so let me write this up again. So I have x1 up to xn. These are IID from a normal distribution mu sigma squared, where this guy is so known. Okay. Now I'm going to, as usual, I'm going to start by doing something like x n bar is 1 over n, I equals 1 over n. Xi, I'm going to start with this kind of this mean random variable. Okay, and then I'm going to get the 95, or the, let's say in so general, the 100 1 minus alpha percent. So confidence. So interval, right, which is going to be a probability for this parameter mu. Okay, and this is going to be equal to 1 minus alpha. Okay, so I'm going to put in two random variables, Ln and Rn, right? So these guys are going to be, this is going to be Ln, this is going to be Rn. These are going to be random variables. Okay, and these are going to, for the randomness in those random variables, that's going to give me this confidence interval for the value mu. Okay. Okay, and let me write them up, and then we can talk about these. So it's going to be xn bar minus z alpha over 2 times sigma over square root n, and this one is going to be xn bar plus z alpha over 2 sigma over square root n. Okay, right? So those two purple expressions are going to be the random variables, and those are those part of those random variables, right? This one is a constant, because I assumed that sigma squared was known. Okay, so I took the square root and I got this. N, this is a parameter based on the number of these, of the random variables, the random observations, right? And this, right, and z alpha n, this is a kind of known constant. You know, I looked this up in a table, depends on the choice of alpha, right? If alpha is 0.05, then, you know, then that is 1.96 roughly. Okay, so what I'm adding and subtracting is a constant, but the random variable is the mean. Okay, and how much I add and subtract, well, that depends on the kind of the standard deviation of the distribution. And because I assumed I knew the variance, then I know what the, you know, how big is the standard deviation, right? So I know so I know that the variance of xn bar is equal to what? What is the variance of xn bar? I know this from the central limit theorem. Not sigma. I need the variance, right? I know the variance of xi, the variance of xi is equal to sigma squared. That's known. I've assumed that's given to me here. Yep. Yeah. So the variance is sigma squared over n. When I take, that's for xn bar, right? When I take an average of random variables, the central limit theorem tells me the variance gets smaller at a rate of 1 over n. The more random variables I get, the better concentration I get here, right? So the variance goes down. I know the variance, so that means that the standard deviation of xn bar is equal to what? Yep. Yeah, so it's the square root of the variance, right? So it's sigma over square root of n, right? Okay, so this is this so the standard deviation. And so I can, in order to calculate, to get to the normal, so random variable, I needed to, if you remember here, okay, if I remember this normal random variable z of n, I needed to divide by the standard deviation that's showing up there in the denominator. But I'm actually I'm working with mu, so I'm instead going to kind of multiply that. You have a comment back there? Yeah, so xn bar is kind of a common notation, and it's always going to be this expression. I've got a set of n random variables, x1 through xn, and I'm taking their average, which again gives me another random variable, right? And this is part of the random variable for ln or rn, right? This is what I'm using as the base, but I'm saying I need to spread it out, right? So I want to take this. I know Zn is a normal, standard normal, so random variable. So I want to kind of do, so I'm just kind of doing some algebra here, right? So I could say that, so if I look at this expression here, one thing I can do is I can say that this is equivalent to adding, so if I just looked at, let's only look at this part of the expression here. So let's say that that the probability that xn bar minus z alpha over 2 sigma square root n, this is less than mu, right? So I'm just looking at half of this for now. I'm going to say this is equal to the probability that xn bar is less than or equal to mu plus z alpha over 2 times so sigma over so square root n. Okay, yeah, question? Yeah, it's an estimator of mu, and in fact, it's an unbiased estimator. Yeah, okay, so the central limit theorem, which we talked about a bit last week, that is I take a bunch of random variables that are from a distribution and I average them together, I get the same expected value, but the variance goes down, right? It might be possible that one random variable is very far away from the expected value, but when I take a bunch of them, the probability that they're all very far away in the same direction is unlikely. And so the central limit theorem tells me as I add these together and concentrate them, that the variance gets smaller. And so my distribution of the average value is more concentrated around the expected value, right? And so this is a property of, this is the central limit theorem. It tells you that as you average stuff, you get lower variance estimators without adding any bias. Okay, and so this is a very powerful thing, and we'll keep seeing examples of why it's useful throughout the semester. This is one instance. Okay. Okay. So what I'm saying here is I've just done some algebra. I've added a constant to both sides here. I can also, now I can say that, this is equal, I can subtract mu from both sides here. Xn bar minus mu is less than or equal to z alpha over 2 times sigma square root of n, right? I've just subtracted mu from both sides, right? So this is the inequality is still going to be true. Mu is also actually a constant here. And I can also divide by sigma over square root n. So I'm going to get sigma n bar minus mu divided by sigma square root n. This is less than z alpha over 2. So does this make sense? I just did some algebra inside this probability, right? There was an inequality. I wanted to know the probability that inequality was true, and these inequalities are all equivalent to each other, right? I added a constant to both sides, right? I divided, in fact, I did that twice, right? Those were the first two steps, and then I divided by a constant which is positive, right? Sigma and square root n are always positive, so I can always divide by a constant, right? So those inequalities are all equal to each other, but the last one is super nice, right? This last one, right here. This last one is actually, well, this is something we understand, right? Because this term inside of here, this is exactly Zn, right? This is a standard normal random variable. Okay, so I've converted it just by algebra into the probability of a standard normal random variable. And now I want to say the probability that standard normal random variable is less than some quantity z alpha over 2. I know that this is exactly equal to alpha over 2. That was the definition of z alpha over 2. Right? Z alpha over 2 was chosen so that that value is that probability is going to be exactly alpha over 2. And because the standard normal, when I did this, I can do this on both halves of those inequalities. It's symmetric. So I have alpha over 2 mass on so either side. Yeah. What? Okay. So yeah, it's related to this, like the standard deviation. The standard deviation tells me how large are those confidence intervals, right? So if you notice in this expression, right, in this expression here, I've taken the mean, the estimator of the mean, xn bar, and I've added or subtracted, on depending if I'm going left or right, by some multiple of the standard deviation. So if the standard deviation is larger, then I need to add or subtract more. It's scaled exactly proportional to the standard deviation. And how much does it go? Times the standard deviation, exactly the z alpha over 2. Right? So that, yeah, just putting these two things together. If the standard deviation of my known distribution, right, that's part I know. I assumed for now that I knew the standard deviation. If I know that that's larger, then then I need to have a larger confidence interval. Okay. And what happens to the confidence interval as the number of samples gets so larger? What's the length of the confidence interval? What's going to happen to it? Okay, well, maybe I'll write this up again. So the normal sigma squared 1 minus alpha. So the confidence interval is going to be the probability that xn bar minus z alpha over 2 square root sigma over square root n. That's going to be less than mu xn bar plus z alpha over 2 times sigma n. This is 1 minus alpha. Right, so I'm given a choice of alpha, say 5%, right, and 0.05. And what happens with the confidence interval as n gets larger? Is it increasing or is it decreasing? Yeah, it's decreasing. This is, yeah. So as you get more data, your interval with the 95% confidence is getting smaller, right? So the interval, right, is xn bar minus z alpha over 2 sigma over square root n xn bar plus z alpha over 2 sigma square root n. So its length here is going to be the subtraction of one from the other, right? The length is going to be xn bar plus z alpha over 2 sigma square root n minus xn bar minus z alpha over 2 sigma square root n, right? And so this I can cancel these guys, and I can factor this guy out. And so what I'm going to get is z alpha over 2 times 2 times sigma over square root n. Okay, so the length of the interval, right, the length of the interval is going to get smaller by a factor of square root n as I get more samples. So if I have 4 times as many samples, it will get half as small. Okay, so it's going to be half the length if I get 4 times as many samples. If I get 16 times as many samples, those will be 1/4 as big. Okay, so I might have originally a distribution that might look like this. This might be, so sigma originally, this is the distribution of f of xi, right? And then let's say I have x and say x bar, say 4. Okay, so the confidence interval originally might have been here. You know, this may have been, this would be like L1 and R1. That might be the 95% so confidence interval. If I average 4 random samples, it should be half as big, right? This was xn bar. Okay, so if I have twice as many samples, then my confidence interval or the distribution, sorry, okay, this picture is not quite, I don't want to draw this picture. This picture is wrong. Okay, those are random variables. That picture is confusing. Okay, but if I have another distribution of 4, okay, of the average of 4 observations, it's going to look like this. It should be about, with 4 random variables, it should be about half as wide. Okay, so this, they're going to have the same mean, and this will be sigma over 2. So that should be half as much. So standard deviation. Okay, it's 5 o'clock. I should stop here, but I want you to think about what was wrong about that picture. I drew up those purple values for the confidence interval, but that was not quite right. Yeah. So if you want to come and tell me or think what you're thinking afterwards, we'll start with that on Thursday. Yeah.
And variables can't draw them.
Great.
Yeah,
good.
You gotta draw a little normal curve for draw.
Yeah. Draw
the sigma comes in the confidence interval.
That's right. Great. Good. So it's starting to sink in. Very good. Yeah. Yep.